Okay, application of filters. Filters come in different shape and different sizes, of course. And many of the membrane filters are used for sterilization because they're very effective in retaining the filtrate. So they also have non-shedding property, meaning the filter material doesn't come off and mixed up with your filtering material, and they don't react a lot, and you can just use it once and throw it away as well. So kind of popular shape of filters are membrane filters. But it's not 100% non-reactive. That has to be tested, of course. Some material could leach out. Okay, so you need to have a careful study done before the approval of your filter use for your manufacturing. And filters may come in, those membrane filters may come in as maybe a flat membrane shape like this, okay, or so the example is a millipore. So this is a millipore flat membrane shape filter, and another shape is pleated into a cylinder or a cartridge filter. So look at this pleated shape. So the filter is kind of folded. That's done to increase the surface size. So the more surface size is there, you can filter out more materials, right? So the pleated filter design is popular as well. So these manufacturers are Kuno, Massener, Millipore, Pal, Sartorius. They manufacture those. Okay, and then capsule filters like this, okay, can be used. And mostly these are disposable, use once and throw away. Okay, now so filter is encapsulated into this shell, okay, rigid shell, so made out of polycarbonate or polypropylene kind of material. So completely disposable, use once and throw it away, right? So that's a possible design. When using a filter cartridge, you need to set up. So filter cartridge, what do you mean? So we're talking about this kind of material. These are cartridges made out of stainless steel material, and you set it up, opening it, and place this filter, and then seal them up with the rubber O-rings and everything. So we're talking about that. So the filter is assembled in the stainless steel housing by first wetting the O-rings. O-rings should make good contact so there's no leakage happening, making sure that the filter is oriented properly. So you don't want to put it upside down, then filtration is not going to happen. Okay. Then the clamps are hand tightened, so you need to tie it up. So see those clamps. So they are kind of hand tightens. Okay. Avoid damaging the filter membrane during the installation. So you have to have an intact shape of filter. That's the most important part. Okay, if there's a damage on the filter, like a hole, puncture, and the materials will go through right there through that damaged part, then there's no filtration happening. Okay, and the filter and housing are then steam sterilized, SIP. Okay, so steam pressurized, hot steam is going to go through and get rid of whatever the contaminants in there, typically by autoclaving the assembly. So if it's small enough, you can place this entire thing into an autoclave. Okay. Filter in stainless steel housing may be sterilized by steam in place. If it's too large to be placed inside of autoclave, then you have to introduce the hot steam into the filter housing. Okay, inlet pressure must be matched to the maximum cartridge temperature with differential pressure control to ensure filter integrity. That means, do not, over pressurize it, then you can damage the filter, and you don't want the damage. Okay, so you have to carefully watch out for the pressure that you're going to apply with the wet steam. And when you do a SIP on your filter housing, pressurization and depressurization should be done slowly, because if you apply too much pressure at once or depressurizing too much, some things could pop out, like you can damage the O-rings and things like that. So you don't want that. Do it gradually, slowly. Okay. In SIP applications, care must be taken that air is replaced by steam, and any condensation that may be happening during sterilization should be removed from the system to allow proper sterilization. So any leftover steam should be dried out. That's what it means, okay, before you use. Validation of sterilization of filter happens with the thermocouples and spot strip located in that identified cold spot within the filter assembly. So during your SIP, you need to check if the SIP process we are doing is really reaching the temperature that's required. If it is really killing the microbials that may be in your filter housing by placing this validation method. Okay. After sterilization, the liquid process filter cartridge may be dried to remove any condensation that happened during the sterilization. So how do you dry it? Maybe compressed gas that is filtered or filters used in the gas purification application must be dried prior to use as well. There's no wet things in there, so you make sure it's all dried. Okay. And then filter validation test. Okay, so after your SIP is done, before you use it, you need to validate if your filter is in good condition. So we're going to talk about the validation methods of different kinds. So in terms of filter validation methods, there are so-called destructive filter validation testing and non-destructive filter validation testing. Okay, so what's the difference? Destructive testing means when you carry out those testing on your filter material, you have to sacrifice your filter. So after testing is done, you cannot use those filters. Okay, so that's what destructive testing is. So normally you do this testing much ahead of your filter use, and then once the testing is done, you cannot use the tested material. So examples are bacterial retention test using actual living bacterial cells that's spiked in your final formulation drug product. Okay, so actually, you sacrifice batch of drug and then you mix that with some bacterial cells, and then you use filter to remove and see, before and after, if you can detect any bacterial cells there or not. So that's a bacterial retention test. So of course, if your filter is deficient, you should not, have any bacterial cells remaining on the filtered material. And the second testing is filter extractable and leachables. Okay, so what it means is there shouldn't be any chemicals, any things that are coming off from your filter material. So that's important, right? If there's a chemicals coming leaching out or extracted out of your filter during your filtration, if they're mixed up with your drug, that's dangerous. So you make sure that your filter material, filter housing is not, adding some additional chemical substance in your drug. So that's the test for that. And third one is the comparability of filter with drug product. What does that mean? If your drug is made out of biological molecule like protein or DNA or RNA, make sure that they don't interact with the filter, and then they are not, once they interact, they don't stay there for a long time. So then if they stay there, you cannot have them come off, then you lose your drug material, right? So that's the comparability test. Okay, so these are all destructive testing, meaning if you do this test, the filter used for the testing is done. You cannot, recover that and use it for your real work. Okay, so bacterial retention test again. So the filter will be challenged with the known amount of bacterial cells, and then see if they are all trapped or removed by your filter. Okay, so the antimicrobial properties of the formulation must be neutralized before adding the microbial challenge. What that means is, the drug or molecule itself, the formulation. Remember, when you talk about formulation, there was a antimicrobial preservative you add to prevent the growth of bacteria. So yeah, you skip that excipient, antimicrobial preservative, when you do your bacterial retention test, because that preservative can kill bacterial cells. Although the filter is not killing and trapping, maybe bacterial cells may be killed by that formulation. You don't want that. So that's what it means. You exclude that for when you do the testing. So the micrograms used for this testing are these kind of species. It's hard to say it. Brevandimonas and Diminuta, that's a species and genus name. They're selected because they have a size of a 0.3 micron, just 0.1 micron above the sterilized filter pore size. Okay, so if your 0.2 micron filter is good, it'll capture it. But if 0.2 micron filter is not good, then this may go through. Then that filter should not be used. Okay, so that's why you select that particular bacterial cell for this testing. So the concentration of this cell should exist about 10 to the 7th, whereas 10 million cells per cubic scale centimeter filter surface area. So you need to add a lot of cells and see if they are all removed by a filter. And then product filter comparability, meaning so your product should not be interacting and then retained by the filter. Okay, so this must be performed to demonstrate that the product does not adversely affect the retention property of the filter, and is accomplished in most cases with the bacterial retention studies, and does not cause the filter to excessively leach material into the product. So like I said before, filter should not leach out any chemicals into your formulation. So filter comparability and extractable studies are performed by a filter manufacturer normally. So manufacturer's responsibility. But although it's a manufacturer of the filter who's responsible, but the product manufacturer, the API product manufacturer, holds the ultimate responsibility for the validity of the data. So you cannot just assume they did a test and the test was good enough. You cannot do that. You have to, find the scientific data and you have to document it just in case FDA has a question about your filter. Okay. So filter manufacturer will provide the information on those and how much negative oxidative substances, and provide the data on the level of extractable obtained with the different models, solvent exposure, and all those things, because manufacturers should have done a lot of studies on their filters. Okay, so that's what it means. And there are non-destructive validation testing. Okay, or you can say in-process filter integrity testing. So these in-process or non-destructive testings are different than the previous destructive testing, because these in-process testings are normally done right before your filtration task, and then it is done again at the end of your test again. So before and after your filter use, these testings are done normally. To demonstrate what? To demonstrate that your filter is intact before you use it, and to demonstrate that yes, it was still intact after you use, so there was no damage during your filtration. So that's the whole purpose of doing this in-process filter integrity testing. Okay, so it's non-destructive, meaning even after the testing is done, your filter can be used. Actually, only after your testing is done, your filter should be used. Also, the after work filter testing should show that your filter was still intact when you filtration is done. Okay, so filter integrity test is done pre-filtration. Normally right before you use for your filtration, and then there's a second filter integrity test done after your filter use. See, it's a pre and post test that are done both before and after your filter use. And bubble point test is one good example, and diffusion or forward flow test. So you will do this bubble point test in the lab. Very simple and cheap testing method you can use. Okay, so your bubble point test will tell you if the bubble point pressure is good enough or not. If the bubble point pressure is not good, that means your filter is damaged, then you should not use that filter. Okay. And then diffusion test is kind of similar as well. What's the diffusion that's happening at your filter? If it's an intact filter, it should be done at a certain rate, a certain pressure. So that's used as the integrity indicator of your filter. Pressure hold test, same way. If your filter is intact, it can hold some pressure compared to damaged filter, which has much lower pressure hold.